Welcome to today's lesson. Today we are on lesson 2-4. Today's learning objective is to expand binomials using the Pascal's triangle. Our language objective is to explain the process when using Pascal's triangle to help us expand binomials. So let's take a look at today's do now. Let's take a look at today's do now. So here you have two questions in which you have to simplify. Pause the video, simplify each, and we will get back together when you are done. All right, so for number one, or the first one, we have x squared plus 6x plus 9. For the second one, more distribution, and we end up at x to the third plus 9x squared plus 27x plus 27. So what if I were to give you x plus 3 to the fourth power? How much fun would you have? So here is our thinking for today. What is the Pascal's triangle? Pascal's triangle. Definition. It's a triangle of numbers where each number is the two numbers above it added together. The edge of the triangle are all ones. How is the triangle formed? So here I have a cake-looking tower, and I'm just going to fill this up. When we are doing Pascal's triangle, the top is a 1, followed by more ones. As the definition says, the edge of the triangle are all ones. So here's my ones. Right now, this looks like nothing. But the awesome thing is that once I set up my triangle, the inner pieces are the previous two added together. So what is 1 plus 1? 2. If I keep filling this up, I add the previous two to get my inner pieces. 1 plus 3 gives me 4. 3 plus 3 gives me 6. 3 plus 1 gives me 4. And I'm slowly going to be filling in the triangle. And this is Pascal's triangle. Literally an infinite amount of ones on the edges with the inner pieces where I'm adding the previous two. So this really looks like nothing, but it's so much in which it's going to help you. So let me look at example 1. Pascal's triangle. Why is Pascal's triangle useful? So it all comes down to the numbers that are within this triangle. So I'm going to set my triangle up with just a few. So I'll start with the top towers, my 3 first ones, and I'm going to slowly start building my triangle. 1, 3, 3, 1. And if you notice, as I increase in rows, I increase in the amount of numbers, right? Plus 1. So I have 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, and 1. And again, keeps going on forever. The reason this is useful is for us doing our do now types of questions. This first one is going to come from a binomial, x plus h to the 0 power. Anything raised to the 0 power is 1. But I'm going to write some stuff that's going to look a little bit weird right now. So this binomial technically would have this one as a coefficient, and we would have x to the 0 power, h to the 0 power. Again, right now does not look like anything. I'm going to keep going. This second piece here, 1 and 1, is also coming from x plus h, some binomial, but this time to the first power. And that is equal to our coefficients of 1 and 1. I'm separating here for a reason. This would be x to the first, h to the 0, plus x to the 0, h to the first. So you're going to slowly start seeing a pattern here. This row here is helping us with x plus h squared. These numbers are our coefficients, our leading coefficients. So we have a 1, a 2, and a 1. And in this case, we will have x to the second. Let's think about where these numbers are coming from, because now we should be seeing some sort of pattern. H to the 0 always, plus x to the first. Those x's start slowly decreasing, and our h's start increasing. In this case, x to the 0, h to the second power. This next row, 1, 3, 3, 1, are our coefficients for if we have a binomial raised to the third power. So here we would have our coefficients of 1, 3, 3, and 1. I would start with x to the third power, h to the 0 power. As I move along, my x's decrease, but my h's exponents increase. X's decrease, h's increase. Here we have 1, 4, 6, 4, 1. Again, comes from a binomial, x plus h, raised to the fourth power. And these are our leading coefficients. I would start with x to the fourth, h to the 0. My x's would decrease and my h's would increase as I move from the left to the right. And the last one, we have x plus h to the fifth. And the pattern would continue. So why is this useful? I'm going to show you in our next example. So example number 2, we are actually going to be using this triangle to help us do our distribution. So let's set up for number 1. It says expand x plus 3 raised to the third power in descending powers of x and simplify your answer. So yes, I can do distribution here, but I am going to practice using the Pascal's triangle. So I'm going to start off by setting my triangle up. So I have 1, 1, and 1. From there, I'm going to start with my 1, add my inner pieces to get my next bunch. So start with the outside 1, add, and we end up at 1. I'm stopping here. The reason I'm stopping here is because I see that second number, and that second number is telling me my exponent, which is the same thing that we're going to be using, right, to the third power. So what this is going to help me with is my leading coefficients. So I know that this is x plus h to the third powers setup. So I'm going to just rewrite what I did in the previous one. X plus h would be 1 x to the third, h to the 0, plus 3 x to the second, h to the first, plus 3 x to the first, h to the second, plus 1 x to the 0, h to the third. So if I look at my binomial, my given binomial, I see that this h is our 3 and x is x. So what I'm going to do is substitute wherever I see an h, the value of 3. Okay, so I substituted. At this point, I'm going to evaluate. So I'm showing a little more work than I normally would. All right, so I evaluated the 3 to the power that was given there. And at this point, let's multiply whatever we can multiply. So we have those. And I'm going to write my answer, my final answer. And I get x cubed plus 9x squared plus 27x plus 27. If you look back at the do now, this is exactly the same thing that we got doing the distribution method. Let's look at number 2. So here we have considered an expansion of x plus 4 to the fourth power. So if you want to do distribution on this, go for it. But as my powers get more large, I really do not want to do distribution. So I'm going to set up my triangle here, and I'm going to stop where I see the second number as a 4. And here is my stop. So this is x plus h to the fourth power. I have a x plus 4 to the fourth, which means that our h is equal to 4. So I'm going to cut the step here by me just substituting the h value right away. All right, so there's my substitution. At this point, I'm going to evaluate as much as I can. All right, so I color coded it so it could be a little bit easier for you to see where my numbers are coming from. Now that I have that, part B wants us to find the x to the third power, which is 16x cubed. Let's try 2 more. So for number 3, we want to expand x minus 5 to the fourth power in descending powers of x and simplify my answer. So I'm going to do the same thing I just did with my triangle. Set myself up just so I have my leading coefficients. All right, so here is the x plus h to the fourth power coefficients, and I have been given x minus 5, which means that our h is a negative 5. So I'm going to substitute that h. All right, so now I'm going to evaluate. All right, so here's my final answer after I multiply each of those color-coded numbers. Number 4, find the x squared term in the expansion of 2x plus 3 to the fifth power. So I am going to again set myself up, and this time I'm looking for the 5. So here we have to do something slightly different. We normally just have an x, but this time we have a 2x. So instead of me just substituting x, I'm going to substitute a 2x everywhere. And our h would be the positive 3. So I'm going to set myself up with the substitution. All right, so there's my substitution, a little bit long, so I had to write my last piece at the bottom. I am going to rewrite this one more time because I have a 2x raised to the fifth power. What that's going to do is take that exponent and distribute it to each of those pieces. So this would be, this 4 would be, and I'm just going to keep going to make this a little more simple. All right, so that is as much as I can do. Now it's just a matter of me inputting these into my calculator and multiplying each piece. All right, and this is my final expansion. Now I can answer the question. It says find the x squared term, which is right here, which means that the x squared term is 1080 x squared. And this is how you use the Pascal's triangle to help you when you have a binomial raised to a certain power. So keep learning, keep growing, and I will see you in our next video.